like 2005 and
And yes, but they get more and more application specific. So there are people that have units named after them that are still alive, and the units have only been in use in the last 10 years or so. Um, but they tend to be in very, very specialized niche applications, because a lot of the most well understood science that you're learning now has been established for 100 years or so. Even the quantum stuff, we don't really touch anything in this class that was after about probably call it the start of World War II. I think Linus Pauling and hybridization is late 30s, early 40s.
What do you think the people inventing stuff now, 100 years from now, will probably be like?
To some extent, there's still a limit in how much material we can cover and how quickly. You know, when you have to start at 5 years old learning how to read, it takes 20 years to get to where you are, right? So I'm not sure how much more that could be compressed. There are some things that are going to be that'll be more well accepted and maybe taught in terms of general terms, but not in terms of like understanding the laws and the math that goes into it. Biochemistry is a really good example of that. Biochemistry was really only discovered and people started working on it in about the late 50s, early 60s. So everything in biochemistry has been discovered since then, including some pretty big things. You know, Watson and Crick they got the credit for discovering DNA, only died. One of them might even still, they're both dead. They only died in like the last, 10 years or so. But yeah, there's going to be some things that are taught differently 100 years from now, but you'll still have to get way into material to be able to learn it. All right, talking about the tests and how you're exhausted after a lab or taking a test. I always use the analogy of it's like working out, right? You have to get in shape. You have to get your brain in shape too to be able to focus on something for 2 to 3 hours at a time. And the take-home test is like me testing you by making you run a marathon. And the in-class test is like me testing you by asking you to run a sprint. Right? So 2 very different things, and people can be good at one and not good at the other. But that doesn't mean that one of those groups of people should be penalized because they're not good at taking tests.
You don't take the test for it, or?
That's an option. I'll have to consider that. But so I will say that the take-home test is a lot of work, but the averages are usually above 90% for people who complete the whole thing. Most people realize it's easier to get your points in the in-class test because it's only 2 hours and it's basic skills that you are all getting used to and getting better. And it's also worth more points. The take-home is only worth 50 points and the in-class test is worth 100. So if you're happy with where your grade is and you think you can do at least as well on the timed test as you did on the midterm, then you can kind of say, I really only need to finish about 3 out of the 5 problems on the take home to keep my A, or 1 out of the 5, depending on how strong your grade is right now. So there's a lot of that element too. The take home test is there to bring your grade up, and if you don't need that, you don't have to do it.
As a student, I just have to do all my work, like print every problem at least.
We might put that to the test. No, it'll be like the ICAs where, if you were in a crunch for time, you would just leave 2E blank, finish everything but 2E, try it if you have time. But
that was 2E. What is the rest of the ICA like? Because I haven't done it.
The rest of it's much easier.
Okay.
The pieces in a problem generally get harder as you go along, but the problems themselves are self-contained. They don't build up. 3 is not harder than 2.
Is it 3 harder?
No, not even. I think it's more basic stoichiometry. I don't even think there's a word problem component to it. And the fourth problem is a word problem, but it's all, what's the word? Conversions. Not even any stoichiometry to it. So, all right, let's practice with this combined law. It's, like I said, it's no different than using any of the others. We just have to know our starting pressure, starting volume, starting temperature. And then if two of those variables are changing, then we can get the, before we actually start plugging that in, let's think realistically though. If the volume is not changing, what happens to this equation?
There's only four variables.
Doesn't matter what the volume is, if it's not changing, then you can divide both sides by that number and it disappears, right? Cancels out because it's on both sides of the equation. So anything that's not changing, you would just basically remove it. And then what you're left with is the equation we just practiced with, P1 over T1, right? If temperature is not changing, then temperature cancels out and you get the Boyle's law that we started with. Right, so this is really just for convenience sake, we can combine them all. You don't necessarily have to use all of these pieces. Anything that's the same, just leave it off. So if we start with P1, inside the balloon is 1.05 ATM. And T1 is 22 Celsius, which is 295 Kelvin. Celsius plus 273. And B1 is 5.00 liters. Then we leave the balloon in the sun and temperature goes up. So T2 is 38 Celsius, which is 311. Then, and our volume, is as balloon warms up, the volume is going to expand a little bit, right? So B2 is 5.08 liters. We're looking for P2. So 1.05 times 295, or times 5 over 295. Then multiply both sides by 311, divide both sides by 5.08. What do we get?
828.
Okay, so that's before you moved over the variables from the other side, right? So 828 equals this still. That's after multiplying these and then dividing by.
I already plugged in all the numbers.
Yeah.
828 torr.
I have 1.0.
So we're not in torr though, we're in atmospheres.
I put it into torr.
Oh,
So
okay.
828.
828
in
torr. If you keep it in atmospheres, what do we get?
1.09.
What is it?
1.09.
1.09.
Would I have got that wrong on the test? Okay.
If I don't specify what units I want it in, then any units are valid. I might have expected most people to leave it in atmospheres because most people don't want to do extra conversions. But it's not wrong. In fact, usually the opposite happens. I expect somebody to, if I ask for the mass, I usually mean in grams. Somebody might not finish converting from milligrams to grams and leave it in milligrams, for instance. Still right, it's just not what I was expecting, so I wouldn't mark that wrong, unless I specifically tell you what units I want. And that seems like a reasonable number, right? I mean, we don't have that much experience with pressure and everything yet, but we have some real world experience with balloons, at least most of us. When a balloon gets hot, it's going to expand a little bit. And the pressure inside is going to go up a little bit. Because what happens when you try to blow up a balloon, it's really easy in the middle, right? And then it gets harder to make it increase. Because as you stretch that plastic more and more, it gets harder to make it expand more. Because the plastic is already about as stretched as it can go. So the pressure inside also goes up. And the volume goes up when the temperature goes up. And that seems like a reasonable amount. You know, we didn't come away with 800 atmospheres. If we did get 800 atmospheres, we probably messed something up. And it could have been something as simple as not putting your units in Kelvin can give you really, really wildly different numbers than what you should get.
So temperature is kind of like Dennis and
Yeah, you got to keep your eye on it.
I. Because it's like if the pressure would go down,
Pressure would go down. Yes, normally pressure would go down if the volume goes up. But because temperature is also increasing, and I've done this before. The reason I wanted to tweak the numbers is the numbers that on slides that are online, you actually get that the pressure drops a little bit. It wound up coming up to like 1.03 instead of 1.09, which is still possible because if you it's still not that out of the ordinary. It could happen in theory if atmospheric pressure dropped. That's not that much for atmospheric pressure to drop a little bit, but it still looked a little bit weird. This makes a little bit more sense intuitively. All right, let's talk about the number of molecules, because at this point, all of the laws that we've dealt with all had to be a closed system. In other words, we're dealing with the same number of gas molecules. We trap gas molecules in the system, and then they will behave according to this rule. But as soon as we change the number of gas molecules, all bets are off, right? You poke a tiny hole in our balloon, this doesn't hold up anymore, right? So number of gas molecules should also play a role here. What's your initial thought about what should happen when we change number of gas molecules? You add gas molecules, what should happen to, say, pressure?
Increase. Is it a closed system? If you're adding it,
it's not a closed system anymore if we're adding molecules. But let's say that we're keeping the temperature and the volume the same. You add gas molecules, what are you doing to the number of collisions?
increasing that.
Right, more cars on the road means more wrecks. So if we're increasing the number of collisions and if temperature is still the same, then they're all still moving the same speed, we would expect the pressure to go up. Or in terms of a balloon, what happens when you add gas molecules to a balloon? What happens to the volume? It pops if you go too far, but it gets bigger, right?
Yeah.
So at a constant pressure, we would say that number of moles should be proportional to volume of a gas. More moles you have, more space it occupies at the same pressure.
And temperature.
And temperature. So remember, temperature is
Proportional to.
so pressure is force over area. Changing volume affects the area. Changing moles affects the total force because you get more collisions. Changing the temperature changes the acceleration because at a higher temperature, everything's moving faster, or the average speed is faster. So by increasing, we're keeping that the same if we're keeping temperature the same, but we're changing the number of collisions by adding more molecules. Or if we decrease the area, we increase the number of, or the total force because it's hitting, we have more hits per square meter. So as long as one variable is held constant, we can throw moles in there too. And because it seems really, probably the most intuitive out of any of these is if you double the number of gas molecules, your pressure should double, right? Or if you're holding your pressure constant, you double gas molecules, your volume should double. So it winds up on the same side of the equation as temperature. When N goes up, pressure goes up. When temperature goes up, pressure goes up. This is the form, if you can, this is Avogadro's law. Avogadro of Avogadro's number. This is actually where he started, was working on gases. And Avogadro's law basically is just this. It's the combined form of all the ones we've looked at so far. This is the way it's written on your equation sheet. Because you don't need to memorize 5 different simple gas laws if you have this. Because what happens when any one variable is constant?
Then it's just not in the equation.
It's not in the equation, right? Because if volume is the same before and after, we can divide both sides by that volume and it goes away. And so if you start from this, any of those other problems we were doing before still work. You say, oh, it says temperature is constant, therefore I'm not including it. And it says volume is constant, I'm not including it. So we have moles and pressure left. Moles change, pressure changes according to this ratio. So let's practice. If a sample of gas has an initial volume of 13.9 liters at a pressure of 1.22 atmospheres. If you then compress it to a volume of 10.3 liters, what's the pressure? Anything that's not explicitly stated, we can assume to be a constant. Right, so it says A sample and B sample. So that's telling us, sort of implying that we're not changing moles.
It's a closed system.
And it's a closed system. And we don't know anything about temperature. So we don't know what temperature is, but we don't really need to if we're assuming it's constant. If we don't see a change happen, we can assume constant temperature. You can even write that when you're showing your work. Assuming constant N and T. So out of our out of Avogadro's law, N and T are the same on both sides, right? If it's constant. So and we're left with Boyle's law that we started with, right? P1 V1 equals P2 V2.
Atmospheres.
And so these actually do, these simple gas laws, they call them simple gas laws because all individually they're pretty easy to prove and to understand the logic behind what's happening. All of the simple gas laws, they do still get used sometimes because in engineering and in things like diesel engines or internal combustion engines, the cycles that they go through, we'll say things like, okay, we're compressing the gas, we're changing the volume, but we're going to assume the temperature is not changing. Or we're assuming that the pressure is not changing and that the volume is. You turn it into a series of either isothermal changes, meaning temperature is constant, or isobaric changes, meaning pressure is constant, or I don't remember the term for when volume is constant. Isovolumetric? Yeah, I think isovolumetric changes. And that, when you put all of those together, you can get a cycle that allows you to extract energy from burning fuel. So they do still have a role, but for the most part, for this class, we're actually going to take it one step further. Because we got to all of our simple gas laws by saying, okay, well, if pressure is equal to a constant times 1 over volume, and then we rearranged it so that they were always equal to the same constant, right? So then we wound up with P1 V1 equals P2 V2 equals the constant. Well, that constant didn't really mean anything, it was just the slope, because there were other things that factored into it. If these are all of the variables that describe a gas, then that means for any gas, we can say they're equal to the same constant. So now we don't even need to worry about keeping anything constant. We don't need this piece because every single gas, making a couple assumptions, every single gas will be equal to the same constant that we call the ideal gas constant. We're making the assumption that the gases don't change phase, they don't interact with, the gas molecules don't interact with each other, and the gas molecules themselves don't take up space, which is a decent approximation under normal conditions, under breathable air conditions. That means every gas, we don't even need P1 V1 over T1 N1. We don't need as long as one variable is held constant, because every gas can be described by pressure volume over moles times temperature, and they all equal R. So capital R is the ideal gas constant. And the units on it look weird, because what are our units? We got a pressure unit times a volume unit over moles over temperature. That's odd. But it means every gas we can reduce to one expression liters times atmospheres per mole Kelvin. And that's a measured number, because it's different if we use different units. If we have our pressure measured in torr, then torr would be in our units here, and this number would be off. Right, so these are the most common units to use in chemistry. And so for these units, this is the value of R we'll use. You can get, there's any number of other value, still the same constant, and it still means this expression is true. For any gas, pressure times volume over N times T equals that same constant. We just don't usually write it like this because nobody likes fractions, right? So if we didn't want to write it with fractions, how would we write it? I think they usually write them in alphabetical order. So we say nRT. This is the what's called the ideal gas law. And it's a pretty good, makes some pretty good assumptions. For the most part, under close to 1 atmosphere, gas molecules are far enough away from each other that they're not interacting with each other and they're not taking up a significant chunk of the volume. Enough temperature to be a gas, but not enough space to be a gas. You're forcing the gas molecules to be as close together as a liquid, even though they have enough energy to be a gas. So that's why things start behaving funny when you do that. And when you go through a phase change, this doesn't apply anymore, because now we don't have a gas. But the nice thing about this, and the number one way that we're going to use this in the test and on work problems, this gives us a way we can solve for moles, right? And if we can solve for moles, what can we do with it?
Make it equal to moles.
Make it equal to moles. Stoichiometry is what I was going for. This is one more way we can get to moles for a stoichiometry problem. If I say, you've got a gas at 1 atmosphere of pressure and it's 5 liters at 25 Celsius, how much product can you make for a given reaction? Well, anytime you have a question, a theoretical yield question, you need moles, right? It's just one more way we can get to moles. So let's try it. And actually this, I don't think you need the ideal gas law to solve this one. Because we're starting with mass. If we have 5 grams of hydrogen and 34.5 grams of carbon monoxide. We can make methanol if we do that. So what's the limiting reactant for these conditions? We start by balancing. Got 4 here, so we need at least 2 of these, and then I think we're good. If you have a starting pressure, what's your final pressure? So start by putting everything in moles. So I'm giving it to you in masses. Should feel like a safety blanket by now, right? Molecular weight's easy to get to moles. Like 2 more sig figs on this one, so it's be some 2.4 or something. 8.
1.
Bingo. And then how about down here?
1.2317.
Moles of CO.
Start.
So, what is the limiting reactant? It's going to be close. I think this is a little bit less than half of the other. So, and we're using it up 2-to-1 rates. I think carbon monoxide is going to run out first, but barely. So 2.481. I'll go the other way.
This one is our 2.
1.2317 moles of CO. And for every 1 mole of CO used is 2 moles H2 used.
It's 2.46. 2.4635.
Moles of H2 used. So reacting all of our carbon monoxide use 2.4635 moles of hydrogen. Do we have enough hydrogen for that?
No.
Yes.
Yes.
We're in
Yes.
excess.
All right, so that tells us what's running out first, right? Using up all of our carbon monoxide didn't use 2.48 moles of hydrogen. So carbon monoxide must be running out first. So that answers the first part of this question. Here's our limiting reactant. If the reaction vessel starts at 1.51 atmospheres, what's the final pressure? Assuming constant temperature and volume. That's helpful, right? That's a clue. So what does that tell you?
It's only pressure per mole.
Right. So we can look at P1 V1 equal over N1 T1 equals P2 V2 over N2 T2. Tells us those go away. So P1 over N1 equals P2 over N2. So if we want to know the final pressure, we need N1 and N2. We have P1. What is N1 going to be? How do we get there?
It is those 2 moles reacting together, right?
Everything's a gas on the reactant side, right? So our total moles of gas
Is those 2 together.
both of them put together. Nothing about any of our gas laws said anything about what the gas is, right? Basically, because the gas molecules are so far apart and don't interact, we can treat them like all gas molecules are the same. It doesn't matter that a gas molecule is hydrogen versus carbon monoxide. They take up the same amount of space and they cause the same amount of pressure because they have the same amount of average kinetic energy if they're the same temperature. So if we have a pressure initially, our pressure is due to all of those moles that are a gas at the beginning. And our final pressure is just going to be based on how many moles we have at the end of everything. So our initial initial number of moles is 2.481 plus 1.232, which gives us 3.71 sounds.
Yeah, listen to her.
Say it again, Ben.
3.7127.
And we only go to the thousandths place here for sig figs, right? And then we did addition, so we're going to keep it to the thousandths place. And we can just say moles of gas, since we're not specifying moles of what now, or moles total. So N1 equals 3.713. N2,
1.2317.
this winds up being kind of like a combined excess reactant question and theoretical yield question, right? So we need to know how many moles of this we make and how many moles of hydrogen are left over. We know we're not going to have any moles of carbon monoxide left over, but we still have two gases because there's a little bit of hydrogen left. And so N2 will come over here. Moles of hydrogen final is going to be what we started with minus what we used. So 0.018. Yeah, that was right. Right? Get this number minus 2.4635, so 4 technically, so to round properly, but it's in the sig figs, right? And how do we know how many moles of methanol we made? How much product did we make? That one's actually pretty easy.
1.317 moles of CH4.
And how do you get there fast?
Just 1-to-1 ratio from CO to CH4O.
1 mole here makes 1 mole there, right? So however many moles of carbon monoxide we started with is how many moles of methanol we're ending with. So if we know N1 and N2 and P1, we should get a final pressure. It's something about half an atmosphere.
0.49. Yeah, actually, the sig figs is 0.5.
So when we solve this for P2, and it's 3 sig figs we're looking for. So 500.
500. 0.49799.
All right, so doing stoichiometry with gases gets a little bit interesting when you have a mixture of things, because to use our gas laws, we have to have the pressure of everything put together. Although sometimes if we're assuming constant temperature and constant volume, since these things are usually reacting in a container with fixed volume, and if they're reacting together, if we can, a lot of times we make the assumption it's a constant temperature, we can actually talk about, instead of being given masses of starting material, we actually can be given pressures. You can have atmospheres of a gas is a way to describe a limiting reactant, right? You can say you have 1.012 atmospheres of CO. And if you know the ideal gas law, you know what temperatures and pressures are, we can find moles from this. So we can just say we have a mixture of these gases and it's this many atmospheres of CO and this many atmospheres of hydrogen. Right, and so that's what's referred to as a partial pressure. That's what I'm looking for. So if we had two gases that don't interact with each other or cause any reaction at all, if you have a canister that has 2 atmospheres of helium and a canister that has 4 atmospheres of argon, if you put them all together, your total atmospheres is going to be 6 atmospheres. So you can just say, I have my partial pressure of helium is 2 atmospheres. My partial pressure of argon is 4 atmospheres. We do this all the time with the actual atmosphere as well, too, because we can say things like 0.8 atmospheres of nitrogen. And because in our atmosphere, nitrogen's 80% of the gas molecules, we can just treat it like it's its own thing. We don't really need the rest of it. It's also why you can scuba dive with dramatically different mixtures of gases as long as the percentage of oxygen is close to the same as what it would be at the surface. And why, you can, think how to phrase that. But essentially, all you really need is that 0.2 atmospheres of oxygen to be able to breathe. Everything else, as long as it's not something that's actively toxic to you, doesn't really matter. Which is why if we terraformed Mars as a species, we wouldn't have nitrogen on Mars. We'd have to get used to living, especially if anybody wanted to walk outside, you'd have to get used to living with very low pressures. But in theory, as long as it was about 0.2 atmospheres of oxygen, that would be doable. Right? Because the rest of them don't really interact with each other.
Too bad you can't put pure oxygen in a tank.
You can, it's just flammable.
Wait, isn't that why some of everything is pure oxygen because it becomes like ozone?
Because you breathe in oxygen when you're scuba diving, you breathe things in at the same pressure as the water around you. And you get 1 atmosphere of pressure for every 12 feet you go down. So you would actually be breathing 2 atmospheres of pressure if you go 12 feet underwater. And so if you had pure oxygen, you'd be actually getting 2 atmospheres. You'd be getting roughly 10 times the amount of oxygen you're supposed to be getting.
Oh, geez.
So they actually cut the concentration of oxygen in scuba diving tanks because you're getting higher pressures when you breathe. And if you go deeper than about 150 feet, they actually have a different blend of gases. Nitrox, yeah, that has even less oxygen in it. I'm not sure, actually, I've never done a nitrox dive. You have to switch over. I think you switch tanks once you hit that. You use a normal scuba tank until you get there, and then switch over to your low oxygen concentration because you're breathing in so many atmospheres with every breath. So cool, fun applications there. And we will end right on time for once. All right, we'll do more practice with PV equals nRT on Tuesday. And any other parts of the ICA that you're still struggling with, we can go over that on Tuesday as well. And we're making good time here.
What would the chemical reactions between the lead and the sugar be?
So it just tells you, so it would basically look like lead by itself and succimer by itself, and then the product would be the 2 of them stuck together.
Oh, okay, that's what I was wondering.
So yeah, you don't really need to write it out. You just need to know that 1 mole of succimer binds 1 mole of lead. There are some similar reactions where you need, say, 3 molecules of the binding agent for every 1 molecule of the metal. And so you would just have a 3-to-1 stoichiometry instead of a 1-to-1 in that case.
Oh, yeah, that makes sense.
Oh, God, I'm gonna do it. Is diving on altitude, like, do you have to do more safety stops or is it different?